In this final trigonometry PowerPoint presentation, we are going to look at some of the basic trig identities. So on this slide, we have all the basic trigonometric identities. We have our quotient identities, our even and odd identities, reciprocal identities, and Pythagorean identities. It's vital that you know your quotient identities. The even and odd ones are also quite important, and the relationship between an even and odd is this, that if you evaluate the negative value of a degree or radian measure, you're going to get the same as if you were evaluating the positive radian and degree measure. So your even functions are cosine and secant. Odd means that if you evaluate the negative value of a radian or degree measure, it ends up giving you the negative value of the positive. So they're opposite. And those are considered odd. All the rest of them are odd. I don't require you to know that for this class in particular, because our focus is on using the identities to simplify functions, and this just doesn't come into play. Hence the fact this is not bolded in blue. The three that I have in blue are the ones that you need to commit to memory, and you probably already have from previous classes. Your reciprocal identities are exactly what they state. They're inverses of one another. That's why we see, for instance, that the sine is 1 over the cosecant, while the cosecant is 1 over the sine. And then you see the similar relationships existing between secant and cosine, cotan and tan. And then we have our Pythagorean identities. We have sine squared plus cosine squared equals 1. We have tangent squared plus 1 equals secant squared. And then we have 1 plus cotangent squared equals cosecant squared. Most students memorize these, but it's important that they just don't appear out of thin air, but you do some type of demonstration that shows where they come from. And so what I'm going to do, particularly with these Pythagorean identities, is just take a few moments to explain where this one comes from, and you could derive then how the other two do. I'm not going to do that now, but I will for this one, and the others follow in a very similar manner. And I'll do that in the next slide. So where does that initial Pythagorean identity come from? Sine squared plus cosine squared equals 1. Well, think about it. It's called the Pythagorean identity. So it's going to have some relationship to the Pythagorean theorem. Well, remembering that sine and cosine generate or come from the unit circle tells us that's where we should start. And the unit circle has a radius of 1. That radius always corresponds to the hypotenuse of any right triangle that you're going to draw. So that would mean that x squared plus y squared has to equal 1 if you're applying the Pythagorean theorem. But here's the deal. We know that x squared corresponds to cosine and y squared is sine. So we simply replace those identities and you get that cosine squared plus sine squared equals 1. And again, this holds because the unit circle always has a radius of 1, where the cosine and sine have to be between -1 and 1, and that radius is therefore always 1 of any inscribed triangle that's there. You could derive the other Pythagorean identities in a similar way, but it's important for students to realize that that identity is really critically linked to the unit circle, and it just didn't appear out of thin air. This is a little unconventional, but what I would like you to do now is to hit the hyperlink that is in this PowerPoint presentation and take 5 minutes. It's really no more than 5 minutes to view this small Khan Academy tutorial that looks at how we can use the Pythagorean identities to simplify some trig functions. I want you to do that first, and then I want you to come back to this PowerPoint and we'll look at some other examples that follow. Example, let's simplify the expression 1 minus cosine of x times 1 plus secant of x times cosine of x. Now sometimes we get a little carried away in mathematics and feel like we've always got to move in a certain order, but remember, multiplication is commutative and associative, so you can multiply in any order you want. What I'm seeing would be the most efficient process would be to take this cosine of x and multiply it into the 1 plus the secant of x. Okay, so let's do that first. When I do that, 1 times cosine of x gives me a cosine of x in that second set of parentheses. And when I multiply cosine times secant, guess what? They're reciprocals. They totally cancel each other out and give us a 1. So we have cosine of x plus 1. Now we have 1 minus cosine of x times cosine of x plus 1. We're going to FOIL these out. When we FOIL them out, we get cosine of x plus 1 minus cosine squared minus cosine of x. Well, these two cosine of x's cancel. We have 1 minus cosine squared of x, which is the same as saying sine of x. And we get that by using our Pythagorean identity that says cosine squared of x plus sine squared of x equals 1, meaning if we move cosine to the other side, sine squared of x equals 1 minus cosine squared of x. The whole purpose of simplifying is to rewrite something in as few terms as possible. And so that's why we want to condense the 1 minus cosine squared of x to sine squared of x. Let's go ahead and look at a couple more examples. Let's simplify the quantity 1 minus sine of a times the quantity of 1 plus the sine of a. Now immediately you see the two similar expressions with opposite signs. And we know we need to FOIL. When you FOIL two binomials with opposite signs, your inside terms always cancel out. And you end up with the difference of the square of the first and the last terms. So we end up with a 1 minus sine squared of a through FOILing, and we get that that is cosine squared of a. It's that easy. If you didn't remember that when you have the same two binomials with opposite signs that the insides cancel out, no worries. Just FOIL and you'll see that they cancel out and you'll still get to the same point. All right, let's look at this last example. 1 over 1 minus cosine of a plus 1 over 1 plus cosine of a equals 2 cosecant squared a. So we want to verify that this identity exists. You work with the more complicated side and try to condense and simplify it to equal the right side. To do that, we need to have a common denominator, and it's just going to be the combination of both of these, which means you're going to have to multiply each one of these fractions by the other. So what ends up happening is that when you multiply both of them by each other, because they look just like the previous example where it's the same binomial with opposite signs, we know our inside terms cancel out and we just square the first and the last. Well, that gives us 1 minus cosine squared of a, which we know through the Pythagorean identity is sine squared of a. So that's what our common denominator is. However, we need to multiply each one of these fractions by what they don't have that the other did have. So we multiply the top of the 1 over 1 minus cosine of a times 1 plus cosine of a. And then for the second one, we multiply it by what its bottom did not have, which is 1 minus cosine of a. We write that common denominator in its most simplified form, which is sine squared. We combine the terms on the top, those two cosines cancel. So we just get 2 over sine squared of a. A simpler way to write this, though, would be in its reciprocal notation, which would be 2 cosecant squared of a.